Hi everyone. Thank you all for coming to my talk. And thank you everyone who organized this conference. Today, I want to talk about how to write a self-hosted Go compiler from scratch. My name is Daisuke. I'm a software engineer at Mercari. Mercari is a C2C marketplace where anyone can buy and sell. I live in Japan, and today I'm speaking from Tokyo. I've been a long-time PHP user, mostly developing web applications, and I wrote some compilers just for fun. Today's goal is to convince you that you can write your own Go compiler, and it's really fun. Here's today's agenda. First, I want to show you demos of how my compiler works, and then I want to tell you my experience of writing a C compiler in Go, writing a Go compiler in Go, and contribution to the official Go compiler, and finally writing another Go compiler in Go. These are my compilers. The first one is 8cc.go. It's a C compiler written in Go. The second one, minigo, and the third one, babygo, are Go compilers written in Go. Each one can compile itself. The architecture of my compilers looks like this. First, my compiler converts source code into an assembly file, and then I use GCC tools. GNU assembler converts the assembly file into an object file, and then GNU linker converts it into a binary executable file. This architecture is common to all my compilers. On the other hand, this is how the official Go works. Go tools include assembler and linker. This is a perfect self-hosting, but I didn't write assembler or linker, so my compiler is not 100% self-hosting yet. Minigo and babygo are targeting x86-64 Linux only. Lexer and parser are handwritten. Standard libraries are made from scratch. The backend design is based on Stack Machine. I'll explain it later. But please don't use it in your production environment, because it's far from production quality for now. There's no garbage collection, no concurrency. There's only minimal error check. Let me demo Hello World. This is a simple Hello World program written in Go. First, I build it by the official Go compiler. And I run it. It works as usual. The file size is more than 1 megabytes. Now let's measure the time. It took 12 milliseconds. It's fast. And then I do the same thing by my compiler. First, I compile my compiler by the official compiler. This babygo is my compiler. And my compiler compiles the Hello World. And it makes an assembly file. Like this. Then I use GNU assembler to convert it into an object file. Then I use GNU linker to convert it into a binary. This hello file is a single static binary. I'll show you. Like this. And I run it. It worked. Let's compare the file sizes. You see, my hello world is just 14 kilobytes. It's about 100 times smaller than the official hello world. Let's measure the time. It took only 5 milliseconds. It's super fast. It's about 2 to 3 times faster than the official hello world. But I must admit that it's not fair comparison because my compiler lacks a lot of features and also the hello world is a very special use case. And I explain how self-hosting works. First, I use the official compiler to convert source code of my compiler into a binary. It's called first generation. And then the first generation compiler converts compiler source code into another compiler, which is called second generation. The second generation compiler can do the same thing, making third generation. The contents of first generation is just an ordinary Go program, so it's different from the contents of second generation. Because second generation is made from my own assembly code, so it's very different. But the contents of third generation is exactly the same as those of second generation. In other words, when the second generation compiles the compiler source code, it outputs itself. It's interesting, isn't it? Let me demo self-hosting. First, I build my compiler by the official compiler. This is the first generation. As I said, this is an ordinary Go program. Then the first generation can compile its source code. And it makes an assembly file. Like this. And I assemble it together with runtime, making babygo 2.0. And LD converts it into a binary. This is the second generation. It's not an ordinary Go program. And let's see the size. The second generation is very small. And when the second generation compiles itself, the third generation is exactly the same as second generation. This is how my self-hosting works. By the way, what did I know before starting this journey? I had zero knowledge about compilers. I didn't major in CS. Actually, my major was literature. I was not very good at Go or C. I was mostly a PHP programmer, and I gave up on trial or Go twice. But I wanted to be better at Go and interested in low-level programming. One day, I encountered with the HCC, a C compiler. It was made by Mr. Rui Ueyama. He is the author of LLD, which is LLVM linker. In a podcast, he told a story of making his own C compiler from scratch and how he achieved self-hosting. The lines of code is about 9,000. I was really excited and impressed by his story. So I immediately cloned the repository and started reading the commit history from the beginning. This is the first commit. It's very small, isn't it? Even though I couldn't understand the full meaning of this code, I was so interested that I continued reading. But actually, I thought reading was not enough to understand it, so instead, I decided to port the commit history. This is my first compiler, hcc.go. It's a C compiler written in Go, and I ported commits from the beginning from C language to Go language. This is how I did it. The direct translation of the commit history is not easy because sometimes one commit was very large, like one commit contained 500 lines. It was not possible for me to translate. So I thought of a strategy. First, I separated the original commits into many smaller commits in C language. It took a lot of time. But once you separate the commits, you can easily understand the meaning of each change. Then it was very easy to translate them from C language to Go language. And I continued this process for over 5 months, and I ported over 100 commits and covered most syntax. I learned how to write C and Go, how the C language works internally, how to read and write assembly code, what stack machines are like, and how similar is C to Go. I learned C and Go at the same time by comparing code of the same meaning. This is an example. Array literal of Go language came from C language. Another example is memory management. A malloc call in C language can be translated into ampersand followed by a struct literal in Go language. This way I learned how Go language interacts with memory by this comparison. Naturally, an idea came into my mind. Can I write a Go compiler by simply using this knowledge? And I started it. I tried writing a Go compiler in Go. The name is minigo. This is the first commit. It's only 4 lines of assembly. It's just a program which exits with status 0. It's so simple. It's not a compiler yet. It's not even Go language. But this is the beginning of everything. And I love this code. In the first day, arithmetic addition worked because I already knew how a compiler works. In the second day, function call worked. In the fifth day, an entire Hello World file worked. In the first month, Fizzbuzz worked. In the second month, it was able to parse itself. I made a rapid progress in the first half. Because Go language is very easy to scan and parse, it's designed as such. Parsers can determine mode only by looking at one token in top level. For example, when a line begins with a type, then we can say it's type declaration. When a line begins with a var, then we can say it's a variable declaration. And types can be read from left to right in a straightforward way, unlike C language. And Go has few historical twists and turns in its syntax. So these are the easy parts in Go compiler. Lecture and parser can be easily implemented. And you can use powerful tools like slice, map, and for range. On the other hand, these are the hard parts. You must implement powerful tools like slice, map, and for range. This is ironic, isn't it? And some data types are larger than a single register. Like string takes 16 bytes, slice takes 24 bytes. So there is no clear answer. Handling them on a stack machine is not trivial. You must design it by yourself. And also runtime features such as coroutine and memory management are very difficult to implement. I learned the spec of the language by writing the compiler, in particular about these things. I think writing a compiler is a very good way to learn a language. I struggled a lot in the last half. In the third month, I implemented pen, map, and interface. In the fourth month, I struggled with a lot of segmentation faults in the second generation compiler. In the fifth month, I still struggled with the same thing. Because, as I explained, the first generation compiler is just an ordinary Go program. But the second generation compiler was made from my assembly code. It had a lot of mistakes. I fought with segmentation faults with GDB. I was fixing a couple of segv bugs every day. But thanks to this experience, I learned to use GDB. Finally, in a 6 month, I won. My compiler successfully compiled itself. Minigo is self-hosted with 10,000 lines of code, and I did it without taking any look at the official compiler. Minigo supports slice, array, struct, map, interface, method call, type assertion, type switch, etc. And after that, I added some more features like environment variables, Go path, importing of third-party libraries, and eliminated libc dependency. Let me introduce some implementations. This is a pen. I borrowed this code from a famous book named Go Programming Language. Luckily, it worked as it is. It was interesting to see that a pen can be written in Go code. This is my first version of malloc. It's super simple. I used a static area. I called it sudo heap. Any program compiled by minigo will have a large static area in its process, and each malloc call consumes a piece of segment from that area. There's no way to free. It's stupid, but it works. In a later version, I rewrote this implementation to use real heap. This is the implementation of a map. Internally, it's just an array of pairs of key and value. Mapget is just a linear search. This is implementation of interface. When a dynamic value is assigned to an interface variable, I store the string representation of that dynamic type. And when the interface value is used in type switch or type assertion, then I compare the string representations of their dynamic types. As I mentioned before, minigo lacks a lot of features, such as garbage collection, coroutine, floating point numbers, multi-platform, etc. Actually, I tried coroutine, but it was extremely difficult. Let me introduce a funny bug. When I implemented a break statement, something strange happened. Can you imagine? When the program reached the break statement, it made a super jump over to the end of the second loop. It's very funny, isn't it? I like this bug. The cause was a mistake in level management in assembly. I fixed it easily. In minigo, there was room for improvement. It was not Go-ish. Internal ABI, application binary interface, is very close to that of C compilers, such as registers assignment in function call. In a sense, it's natural, because all of my knowledge came from a C compiler. And initially, I started with a null-terminated string and libc dependency. I changed the fundamental design after a lot of effort, like I converted null-terminated string into slice-like struct, and finally, I eliminated libc dependency. But I wish I had done it from the beginning. Code generation is a chaos, especially backend of assignment is super complicated due to my poor understanding of stack machine. At that time, I needed a change, so I tried a different thing. After the minigo project, I started to look at the official Go compiler, and to my surprise, I found myself being able to understand some parts. Because I already had an overall map in my mind about what compilers look like, I could read the code by thinking what's different between mine and theirs. I was interested in how size of each embedded type is designed, so I took a look at these files. This is the code which sets the size of slice. I felt something was strange. I wondered why the size of a slice is named size of array. And I found some other variables for slice had the prefix of array. Probably this is by historical reasons, but could we improve these? So I tried submitting a patch to rename array to slice in those variables. It's approved without any argument, and it's merged into Go 1.4. I was happy and took a rest from compilers for half a year. But still, there were some lingering questions in my mind. Could I do self-host much more easily if I try another one? What would it be like to take a different approach? Like if I started without libc dependency from the beginning? If I used Go's parser? What is the ideal stack machine? At that time, chibicc was born. It's another C compiler made by Mr. Rui Ueyama, with more sophisticated design and a much simpler stack machine. It was so beautiful that I wanted to make another compiler. And I started writing another Go compiler in Go. The name is babygo. This time, the theme was, how do I achieve self-hosting with less code? This is the first commit. Again, this is a program which just exists. But can you see the difference from that one in my previous compiler? In babygo, there's no main function, and it's directly hitting syscall. which means it started without depending on libc. In babygo, I took different approaches, less features, better stack machine, more Go-like, and I made an innovation in the order of implementation. Less features. I kept babygo as small as possible. I omitted some features such as map, interface, method, packaging system, and so on, because these are not needed for self-hosting. I designed a better stack machine. It's chibicc style. The basic idea is this. Whenever an expression appears, we just push its value onto stack memory and pop it before its operation. By this design, code generation of assignment got much better. This is how an assignment of y to x works. First, we calculate the address of x and push it. Then we calculate the address of y and push it. Then we pop the address of y and fetch the content and push it. And finally, we store the value of y to the address of x. The advantage of this design is that left-hand side and right-hand side are treated in the same way. So we can apply this logic to any form of assignment. I wanted babygo to be more Go-like internally. I kept it independent from libc. I designed string as a combination of a pointer and a length, and I made ABI more similar to that of the official Go. This is my handwritten syscall. The function syscall.syscall is implemented in assembly, and a Go code in runtime can call it. I borrowed this design from the official standard libraries, and this mechanism helped me avoid using libc. As for the ABI, I mimicked the official Go's ABI partially. In this example, parameter A is located at +8 position of stack pointer, and parameter B is located at +16 position of stack pointer. This is the ABI of babygo. Seemingly, the assembly code looks very different, but the memory layout of parameter A and parameter B are very similar to that of the official Go. I made an innovation in the order of implementation. As I said, in Go compiler, scanner and parser are easy to write, but code generation is very difficult. In my opinion, the design of code generation is critical to the success of the project. So I wrote code generation first with using Go's parser and Go's AST, and I verified whether the chibicc's stack machine works in the Go compiler, and it worked. But the dependency on Go/packages makes self-hosting very difficult, because the Go/packages depend on a lot of other packages like FMT, OS, and runtime, which include various kinds of grammar. So, after implementing a certain amount of features in the first generation compiler, I started writing a second generation compiler from scratch. I ported a scanner and parser from the Go/packages to my compiler with using the minimum grammar that the first generation compiler supports. The biggest advantage of this method is that if the code gen in the first generation compiler has any bugs, we can find them early while writing the second generation compiler. Then we can fix them easily. After implementing scanner and parser and codegen in the second generation compiler, finally it was able to compile itself. Yeah, I achieved self-host again. Compared with my previous compiler, with half time, with half lines of code, this time it's less than 5,000, and with much higher readability. Conclusion: writing a Go compiler is not that hard as long as you don't pursue a perfect one. Making something is the best way to understand it. This experience helped me understand and contribute to the official compiler. If you want to learn compilers, I'd recommend babygo or chibicc as learning materials. Replaying the commit history is a very good way to learn. You don't need to be a computer science expert beforehand. You can just get started. Let's make your own Go compiler. I want to say thank you to Ri for giving us great learning materials, and to my colleagues for helping me make this presentation. Thank you for listening.